Nitrogen. Nitrogen is a chemical element with symbol N and atomic number 7. It was first discovered and isolated by Scottish physician Daniel Rutherford in 1772. Although Carl Wilhelm Scheele and Henry Cavendish had independently done so at about the same time, Rutherford is generally accorded the credit because his work was published first. The name nitrogène was suggested by French chemist Jean-Antoine-Claude Chaptal in 1790, when it was found that nitrogen was present in nitric acid and nitrates. Antoine Lavoisier suggested instead the name azote, from the Greek zeta omega tau iota kappa no life, as it is an asphyxiant gas. This name is instead used in many languages, such as French, Russian, and Turkish, and appears in the English names of some nitrogen compounds such as hydrazine, azides, and azote compounds. Nitrogen is the lightest member of group 15 of the periodic table, often called the pnictogens. The name comes from the Greek pi nu gamma epsilon iota nu to choke, directly referencing nitrogen's asphyxiating properties. It is a common element in the universe, estimated at about 7th in total abundance in the Milky Way and the Solar System. At standard temperature and pressure, 2 atoms of the element bind to form dinitrogen, a colorless and odorless diatomic gas with the formula N2. Dinitrogen forms about 78% of Earth's atmosphere, making it the most abundant uncombined element. Nitrogen occurs in all organisms, primarily in amino acids, in the nucleic acids and in the energy transfer molecule adenosine triphosphate. The human body contains about 3% nitrogen by mass, the 4th most abundant element in the body after oxygen, carbon, and hydrogen. The nitrogen cycle describes movement of the element from the air, into the biosphere and organic compounds, then back into the atmosphere. Many industrially important compounds, such as ammonia, nitric acid, organic nitrates, and cyanides, contain nitrogen. The extremely strong triple bond in elemental nitrogen, the second strongest bond in any diatomic molecule after carbon monoxide, dominates nitrogen chemistry. This causes difficulty for both organisms and industry in converting N2 into useful compounds, but at the same time means that burning, exploding, or decomposing nitrogen compounds to form nitrogen gas releases large amounts of often useful energy. Synthetically produced ammonia and nitrates are key industrial fertilizers, and fertilizer nitrates are key pollutants in the eutrophication of water systems. Apart from its use in fertilizers and energy stores, nitrogen is a constituent of organic compounds as diverse as Kevlar used in high-strength fabric and cyanoacrylate used in superglue. Nitrogen is a constituent of every major pharmacological drug class, including antibiotics. Many drugs are mimics or prodrugs of natural nitrogen-containing signal molecules. For example, the organic nitrates nitroglycerin and nitroprusside control blood pressure by metabolizing into nitric oxide. Many notable nitrogen-containing drugs, such as the natural caffeine and morphine or the synthetic amphetamines, act on receptors of animal neurotransmitters. Nitrogen compounds have a very long history, ammonium chloride having been known to Herodotus. They were well known by the Middle Ages. Alchemists knew nitric acid as aqua fortis, as well as other nitrogen compounds such as ammonium salts and nitrate salts. The mixture of nitric and hydrochloric acids was known as aqua regia, celebrated for its ability to dissolve gold, the king of metals. The discovery of nitrogen is attributed to the Scottish physician Daniel Rutherford in 1772, who called it noxious air. Though he did not recognize it as an entirely different chemical substance, he clearly distinguished it from Joseph Black's fixed air, or carbon dioxide. The fact that there was a component of air that does not support combustion was clear to Rutherford, although he was not aware that it was an element. Nitrogen was also studied at about the same time by Carl Wilhelm Scheele, Henry Cavendish, and Joseph Priestley, who referred to it as burnt air or phlogisticated air. Nitrogen gas was inert enough that Antoine Lavoisier referred to it as mephitic air or azote, from the Greek word zeta omega tau iota kappa, no life. In an atmosphere of pure nitrogen, animals died and flames were extinguished. Though Lavoisier's name was not accepted in English, since it was pointed out that almost all gases are mephitic, it is used in many languages and still remains in English in the common names of many nitrogen compounds, such as hydrazine and compounds of the azide ion. Finally, it led to the name pnictogens for the group headed by nitrogen, from the Greek pi nu gamma epsilon iota nu to choke. The English word nitrogen entered the language from the French nitrogène, coined in 1790 by French chemist Jean-Antoine Chaptal, from the French niter and the French suffix gene, producing, from the Greek gamma epsilon nu. Chaptal's meaning was that nitrogen is the essential part of nitric acid, which in turn was produced from niter. In earlier times, niter had been confused with Egyptian natron called nu taro omicron nu in Greek, which, despite the name, contained no nitrate. The earliest military, industrial, and agricultural applications of nitrogen compounds used saltpeter, most notably in gunpowder, and later as fertilizer. In 1910, Lord Rayleigh discovered that an electrical discharge in nitrogen gas produced active nitrogen, a monatomic allotrope of nitrogen. The whirling cloud of brilliant yellow light produced by his apparatus reacted with mercury to produce explosive mercury nitride. For a long time, sources of nitrogen compounds were limited. Natural sources originated either from biology or deposits of nitrates produced by atmospheric reactions. Nitrogen fixation by industrial processes like the Frank-Caro process and Haber-Bosch process eased this shortage of nitrogen compounds, to the extent that half of global food production now relies on synthetic nitrogen fertilizers. At the same time, use of the Ostwald process to produce nitrates from industrial nitrogen fixation allowed the large-scale industrial production of nitrates as feedstock in the manufacture of explosives in the world wars of the 20th century. A nitrogen atom has 7 electrons. In the ground state, they are arranged in the electron configuration 1s2 2s2 2p1x 2p1y 2p1z. It therefore has 5 valence electrons in the 2s and 2p orbitals, 3 of which are unpaired. It has one of the highest electronegativities among the elements, exceeded only by chlorine, oxygen, and fluorine. Following periodic trends, its single bond covalent radius of 71 pm is smaller than those of boron and carbon, while it is larger than those of oxygen and fluorine. The nitride anion, N3, is much larger at 146 pm, similar to that of the oxide and fluoride anions. The first 3 ionization energies of nitrogen are 1.402, 2.856, and 4.577 mJ/mol1, and the sum of the fourth and fifth is 16.920 mJ/mol1. Due to these very high figures, nitrogen has no simple cationic chemistry. The lack of radial nodes in the 2p subshell is directly responsible for many of the anomalous properties of the first row of the p block, especially in nitrogen, oxygen, and fluorine. The 2p subshell is very small and has a very similar radius to the 2s shell, facilitating orbital hybridization. It also results in very large electrostatic forces of attraction between the nucleus and the valence electrons in the 2s and 2p shells, resulting in very high electronegativities. Hypervalency is almost unknown in the 2p elements for the same reason, because the high electronegativity makes it difficult for a small nitrogen atom to be a central atom in an electron-rich 3-center 4-electron bond, since it would tend to attract the electrons strongly to itself. Thus, despite nitrogen's position at the head of group 15 in the periodic table, its chemistry shows huge differences from that of its heavier congeners phosphorus, arsenic, antimony, and bismuth. Nitrogen may be usefully compared to its horizontal neighbors carbon and oxygen, as well as its vertical neighbors in the pnictogen column. Although each period 2 element from lithium to nitrogen shows some similarities to the period 3 element in the next group from magnesium to sulfur, their degree drops off quite abruptly past the boron-silicon pair, so that the similarities of nitrogen to sulfur are mostly limited to sulfur nitride ring compounds when both elements are the only ones present. Nitrogen resembles oxygen far more than it does carbon, with its high electronegativity and concomitant capability for hydrogen bonding and the ability to form coordination complexes by donating its lone pairs of electrons. It does not share carbon's proclivity for catenation, with the longest chain of nitrogen yet discovered being composed of only 8 nitrogen atoms, N equals N and N equals NPH. One property nitrogen does share with both its horizontal neighbors is its preferentially forming multiple bonds, typically with carbon, nitrogen, or oxygen atoms, through pp-pp interactions. Thus, for example, nitrogen occurs as diatomic molecules and thus has very much lower melting and boiling points than the rest of its group, as the N2 molecules are only held together by weak van der Waals interactions and there are very few electrons available to create significant instantaneous dipoles. This is not possible for its vertical neighbors. Thus, the nitrogen oxides, nitrites, nitrates, nitro, nitroso, azo, and diazo compounds, azides, cyanates, thiocyanates, and iminoderivatives find no echo with phosphorus, arsenic, antimony, or bismuth. By the same token, however, the complexity of the phosphorus oxoacids finds no echo with nitrogen. Nitrogen has two stable isotopes, 1,4N and 1,5N. The first is much more common, making up 99.634% of natural nitrogen, and the second makes up the remaining 0.366%. This leads to an atomic weight of around 14.007 U. Both of these stable isotopes are produced in the CNO cycle in stars, but 1,4N is more common as its neutron capture is the rate-limiting step. 1,4N is one of the 5 stable odd nuclides, the other 4 are 2H, 6Li, 10B, and 180MTA. The relative abundance of 1,4N and 1,5N is practically constant in the atmosphere but can vary elsewhere, due to natural isotopic fractionation from biological redox reactions and the evaporation of natural ammonia or nitric acid. Biologically mediated reactions strongly control nitrogen dynamics in the soil. These reactions typically result in 1,5N enrichment of the substrate and depletion of the product. The heavy isotope 1,5N was first discovered by S.M. Node in 1929, soon after heavy isotopes of the neighboring elements oxygen and carbon were discovered. It presents one of the lowest thermal neutron capture cross-sections of all isotopes. It is frequently used in nuclear magnetic resonance spectroscopy to determine the structures of nitrogen-containing molecules, due to its fractional nuclear spin of 1/2, which offers advantages for NMR such as narrower line width. 1,4N, though also theoretically usable, has an integer nuclear spin of 1 and thus has a quadrupole moment that leads to wider and less useful spectra. 1,5N NMR nevertheless has complications not encountered in the more common 1H and 1,3C NMR spectroscopy. The low natural abundance of 1,5N significantly reduces sensitivity, a problem which is only exacerbated by its low gyromagnetic ratio. As a result, the signal-to-noise ratio for 1H is about 300 times as much as that for 1,5N at the same magnetic field strength. This may be somewhat alleviated by isotopic enrichment of 1,5N by chemical exchange or fractional distillation. 15N enriched compounds have the advantage that under standard conditions, they do not undergo chemical exchange of their nitrogen atoms with atmospheric nitrogen, unlike compounds with labeled hydrogen, carbon, and oxygen isotopes that must be kept away from the atmosphere. The 15N-14N ratio is commonly used in stable isotope analysis in the fields of geochemistry, hydrology, paleoclimatology, and paleoceanography, where it is called delta 1,5N. Of the 10 other isotopes produced synthetically, ranging from 1,2N to 2,3N, 1,3N has a half-life of 10 minutes and the remaining isotopes have half-lives on the order of seconds or even milliseconds. No other nitrogen isotopes are possible as they would fall outside the nuclear drip lines, leaking out a proton or neutron. Given the half-life difference, 1,3N is the most important nitrogen radioisotope, being relatively long-lived enough to use in positron emission tomography, although its half-life is still short and thus it must be produced at the venue of the PET, for example in a cyclotron via proton bombardment of 1,6O producing 1,3N and an alpha particle. The radioisotope 1,6N is the dominant radionuclide in the coolant of pressurized water reactors or boiling water reactors during normal operation, and thus it is a sensitive and immediate indicator of leaks from the primary coolant system to the secondary steam cycle, and is the primary means of detection for such leaks. It is produced from 1,6O via an reaction in which the 1,6O atom captures a neutron and expels a proton. It has a short half-life of about 7.1 s, but during its decay back to 160 produces high-energy gamma radiation. Because of this, access to the primary coolant piping in a press-sunrised water reactor must be restricted during reactor power operation. Atomic nitrogen, also known as active nitrogen, is highly reactive, being a triradical with 3 unpaired electrons. Free nitrogen atoms easily react with most elements to form nitrides, and even when 2 free nitrogen atoms collide to produce an excited N2 molecule, they may release so much energy on collision with even such stable molecules as carbon dioxide and water to cause homolytic fission into radicals such as CONO or ONH. Atomic nitrogen is prepared by passing an electric discharge through nitrogen gas at 0.12 mmHg, which produces atomic nitrogen along with a peach yellow emission that fades slowly as an afterglow for several minutes even after the discharge terminates. Given the great reactivity of atomic nitrogen, elemental nitrogen usually occurs as molecular N2, dinitrogen. This molecule is a colorless, odorless, and tasteless diamagnetic gas at standard conditions. It melts at 210 degrees C and boils at 196 degrees C. Dinitrogen is mostly unreactive at room temperature, but it will nevertheless react with lithium metal and some transition metal complexes. This is due to its bonding, which is unique among the diatomic elements at standard conditions in that it has an N-N triple bond. Triple bonds have short bond lengths and high dissociation energies, and are thus very strong, explaining dinitrogen's chemical inertness. There are some theoretical indications that other nitrogen oligomers and polymers may be possible. If they could be synthesized, they may have potential applications as materials with a very high energy density, that could be used as powerful propellants or explosives. This is because they should all decompose to dinitrogen, whose N-N triple bond is much stronger than those of the N=N double bond or the N-N single bond. Indeed, the triple bond has more than thrice the energy of the single bond. A great disadvantage is that most neutral polynitrogens are not expected to have a large barrier towards decomposition, and that the few exceptions would be even more challenging to synthesize than the long-sought but still unknown tetrahedrane. This stands in contrast to the well-characterized cationic and anionic polynitrogens azide, pentazonium, and pentazolide. Under extremely high pressures and high temperatures, as produced in a diamond anvil cell, nitrogen polymerizes into the single-bonded cubic gauge crystal structure. This structure is similar to that of diamond, and both have extremely strong covalent bonds, resulting in its nickname nitrogen diamond. At atmospheric pressure, molecular nitrogen condenses at 77 K and freezes at 63 K into the beta-hexagonal close-packed crystal allotropic form. Below 35.4 K nitrogen assumes the cubic crystal allotropic form. Liquid nitrogen, a colorless fluid resembling water in appearance, but with 80.8% of the density, is a common cryogen. Solid nitrogen has many crystalline modifications. It forms a significant dynamic surface coverage on Pluto and outer moons of the solar system such as Triton. Even at the low temperatures of solid nitrogen it is fairly volatile and can sublime to form an atmosphere, or condense back into nitrogen frost. It is very weak and flows in the form of glaciers, and on Triton geysers of nitrogen gas come from the polar ice cap region. The first example of a dinitrogen complex to be discovered was 2+, and soon many other such complexes were discovered. These complexes, in which a nitrogen molecule donates at least one lone pair of electrons to a central metal cation, illustrate how N2 might bind to the metal in nitrogenase and the catalyst for the Haber process. These processes involving dinitrogen activation are vitally important in biology and in the production of fertilizers. Dinitrogen is able to coordinate to metals in 5 different ways. The more well-characterized ways are the end-on MNN and MNNM, in which the lone pairs on the nitrogen atoms are donated to the metal cation. The less well-characterized ways involve dinitrogen donating electron pairs from the triple bond, either as a bridging ligand to 2 metal cations or to just one. The fifth and unique method involves triple coordination as a bridging ligand, donating all 3 electron pairs from the triple bond. A few complexes feature multiple N2 ligands and some feature N2 bonded in multiple ways. Since N2 is isoelectronic with carbon monoxide and acetylene, the bonding in dinitrogen complexes is closely allied to that in carbonyl compounds. Although N2 is a weaker sigma donor and pi acceptor than CO, theoretical studies show that sigma donation is a more important factor allowing the formation of the Mn bond than pi back donation, which mostly only weakens the Nn bond, and end-on donation is more readily accomplished than side-on donation. Today, dinitrogen complexes are known for almost all the transition metals, accounting for several hundred compounds. They are normally prepared by three methods. Occasionally the Nn bond may be formed directly within a metal complex, for example by directly reacting coordinated ammonia with nitrous acid, but this is not generally applicable. Most dinitrogen complexes have colors within the range white, yellow, orange, red, brown. A few exceptions are known, such as the blue. Nitrogen bonds to almost all the elements in the periodic table except the first three noble gases, helium, neon, and argon, and some of the very short-lived elements after bismuth, creating an immense variety of binary compounds with varying properties and applications. Many binary compounds are known, with the exception of the nitrogen hydrides, oxides, and fluorides. These are typically called nitrides. Many stoichiometric phases are usually present for most elements. They may be classified as salt-like, covalent, diamond-like, and metallic, although this classification has limitations generally stemming from the continuity of bonding types instead of the discrete and separate types that it implies. They are normally prepared by directly reacting a metal with nitrogen or ammonia, or by thermal decomposition of metal amides. Many variants on these processes are possible. The most ionic of these nitrides are those of the alkali metals and alkaline earth metals, Li3N and M3N2. These can formally be thought of as salts of the N3 anion, although charge separation is not actually complete even for these highly electropositive elements. However, the alkali metal azides NaN3 and Kn3, featuring the linear N3 anion, are well known, as are Sr2 and Ba2. Azides of the B subgroup metals are much less ionic, have more complicated structures, and detonate readily when shocked. Many covalent binary nitrides are known. Examples include cyanogen 2, triphosphorus pentanitride, disulfur dinitride, and tetrasulfur tetranitride. The essentially covalent silicon nitride and germanium nitride are also known. Silicon nitride in particular would make a promising ceramic if not for the difficulty of working with and sintering it. In particular, the group 13 nitrides, most of which are promising semiconductors, are isoelectronic with graphite, diamond, and silicon carbide and have similar structures. Their bonding changes from covalent to partially ionic to metallic as the group is descended. In particular, since the Bn unit is isoelectronic to Cc, and carbon is essentially intermediate in size between boron and nitrogen, much of organic chemistry finds an echo in boron-nitrogen chemistry, such as in borazine. Nevertheless, the analogy is not exact due to the ease of nucleophilic attack at boron due to its deficiency in electrons, which is not possible in a wholly carbon-containing ring. The largest category of nitrides are the interstitial nitrides of formulae Mn, M2n, and M4n, where the small nitrogen atoms are positioned in the gaps in a metallic cubic or hexagonal close-packed lattice. They are opaque, very hard, and chemically inert, melting only at very high temperatures. They have a metallic luster and conduct electricity as do metals. They hydrolyze only very slowly to give ammonia or nitrogen. The nitride anion is the strongest pi donor known amongst ligands. Nitrate O complexes are generally made by thermal decomposition of azides or by deprotonating ammonia, and they usually involve a terminal N3 group. The linear azide anion, being isoelectronic with nitrous oxide, carbon dioxide, and cyanate, forms many coordination complexes. Further catenation is rare, although N44 is known. Industrially, ammonia is the most important compound of nitrogen and is prepared in larger amounts than any other compound, because it contributes significantly to the nutritional needs of terrestrial organisms by serving as a precursor to food and fertilizers. It is a colorless alkaline gas with a characteristic pungent smell. The presence of hydrogen bonding has very significant effects on ammonia, conferring on it its high melting and boiling points. As a liquid, it is a very good solvent with a high heat of vaporization, that also has a low viscosity and electrical conductivity and high dielectric constant, and is less dense than water. However, the hydrogen bonding in NH3 is weaker than that in H2O due to the lower electronegativity of nitrogen compared to oxygen and the presence of only one lone pair in NH3 rather than two in H2O. It is a weak base in aqueous solution. Its conjugate acid is ammonium, NH+4. It can also act as an extremely weak acid, losing a proton to produce the amide anion, NH2. It thus undergoes self-dissociation, similar to water, to produce ammonium and amide. Ammonia burns in air or oxygen, though not readily, to produce nitrogen gas. It burns in fluorine with a greenish-yellow flame to give nitrogen trifluoride. Reactions with the other nonmetals are very complex and tend to lead to a mixture of products. Ammonia reacts on heating with metals to give nitrides. Many other binary nitrogen hydrides are known, but the most important are hydrazine and hydrogen azide. Although it is not a nitrogen hydride, hydroxylamine is similar in properties and structure to ammonia and hydrazine as well. Hydrazine is a fuming, colorless liquid that smells similarly to ammonia. Its physical properties are very similar to those of water. Despite it being an endothermic compound, it is kinetically stable. It burns quickly and completely in air very exothermically to give nitrogen and water vapor. It is a very useful and versatile reducing agent and is a weaker base than ammonia. It is also commonly used as a rocket fuel. Hydrazine is generally made by reaction of ammonia with alkaline sodium hypochlorite in the presence of gelatin or glue. The reason for adding gelatin is that it removes metal ions such as Cu2+ that catalyses the destruction of hydrazine by reaction with chloramine to produce ammonium chloride and nitrogen. Hydrogen azide was first produced in 1890 by the oxidation of aqueous hydrazine by nitrous acid. It is very explosive and even dilute solutions can be dangerous. It has a disagreeable and irritating smell and is a potentially lethal poison. It may be considered the conjugate acid of the azide anion, and is similarly analogous to the hydrohalic acids. All four simple nitrogen trihalides are known. A few mixed halides and hydrohalides are known, but are mostly unstable and uninteresting. Examples include NClF2, NCl2F, NBrF2, NF2H, NCl2H, and NClH2. 5 nitrogen fluorides are known. Nitrogen trifluoride is a colorless and odorless gas that is thermodynamically stable, and most readily produced by the electrolysis of molten ammonium fluoride dissolved in anhydrous hydrogen fluoride. Like carbon tetrafluoride, it is not at all reactive and is stable in water or dilute aqueous acids or alkalis. Only when heated does it act as a fluorinating agent, and it reacts with copper, arsenic, antimony, and bismuth on contact at high temperatures to give tetrafluorohydrazine. The cations NF+4 and N2F+3 are also known, as is ONF3, which has aroused interest due to the short NO distance implying partial double bonding and the highly polar and long NF bond. Tetrafluorohydrazine, unlike hydrazine itself, can dissociate at room temperature and above to give the radical NF2. Fluorine azide is very explosive and thermally unstable. Dinitrogen difluoride exists as thermally interconvertible cis and trans isomers, and was first found as a product of the thermal decomposition of FN3. Nitrogen trichloride is a dense, volatile, and explosive liquid whose physical properties are similar to those of carbon tetrachloride, although one difference is that NCl3 is easily hydrolyzed by water while CCl4 is not. It was first synthesized in 1811 by Pierre-Louis Dulong, who lost 3 fingers and an eye to its explosive tendencies. As a dilute gas it is less dangerous and is thus used industrially to bleach and sterilize flour. Nitrogen tribromide, first prepared in 1975, is a deep red, temperature-sensitive, volatile solid that is explosive even at 100 degrees C. Nitrogen triiodide is still more unstable and was only prepared in 1990. Its adduct with ammonia, which was known earlier, is very shock sensitive. It can be set off by the touch of a feather, shifting air currents, or even alpha particles. For this reason, small amounts of nitrogen triiodide are sometimes synthesized as a demonstration to high school chemistry students or as an act of chemical magic. Chlorine azide and bromine azide are extremely sensitive and explosive. Two series of nitrogen oxohalides are known, the Nitrosyl Halides and the Nitrill Halides. The first are very reactive gases that can be made by directly halogenating nitrous oxide. Nitrosyl fluoride is colorless and a vigorous fluorinating agent. Nitrosyl chloride behaves in much the same way and has often been used as an ionizing solvent. Nitrosyl bromide is red. The reactions of the nitrill halides are mostly similar. Nitrill fluoride and nitrill chloride are likewise reactive gases and vigorous halogenating agents. Nitrogen forms 9 molecular oxides, some of which were the first gases to be identified: N2O, NO, N2O3, NO2, N2O4, N2O5, N4O, and N3. All are thermally unstable towards decomposition to their elements. One other possible oxide that has not yet been synthesized is oxiditrazole, an aromatic ring. Nitrous oxide, better known as laughing gas, is made by thermal decomposition of molten ammonium nitrate at 250 degrees C. This is a redox reaction and thus nitric oxide and nitrogen are also produced as byproducts. It is mostly used as a propellant and aerating agent for sprayed canned whipped cream, and was formerly commonly used as an anesthetic. Despite appearances, it cannot be considered to be the anhydride of hyponitrous acid because that acid is not produced by the dissolution of nitrous oxide in water. It is rather unreactive and has the unsymmetrical structure NO. Above 600 degrees C it dissociates by breaking the weaker NO bond. Nitric oxide is the simplest stable molecule with an odd number of electrons. In mammals, including humans, it is an important cellular signaling molecule involved in many physiological and pathological processes. It is formed by catalytic oxidation of ammonia. It is a colorless paramagnetic gas that, being thermodynamically unstable, decomposes to nitrogen and oxygen gas at 1100–1200 degrees C. Its bonding is similar to that in nitrogen, but one extra electron is added to a pi* antibonding orbital and thus the bond order has been reduced to approximately 2.5, hence dimerization to O equals NN equals O is unfavorable except below the boiling point because it does not actually increase the total bond order and because the unpaired electron is delocalized across the NO molecule, granting it stability. There is also evidence for the asymmetric red dimer O equals N when nitric oxide is condensed with polar molecules. It reacts with oxygen to give brown nitrogen dioxide and with halogens to give nitrosyl halides. It also reacts with transition metal compounds to give nitrosyl complexes, most of which are deeply colored. Blue dinitrogen trioxide is only available as a solid because it rapidly dissociates above its melting point to give nitric oxide, nitrogen dioxide, and dinitrogen tetroxide. The latter two compounds are S.